The Fourier transform is one of the most important functions when it comes to signal processing, possibly the most important. What it does is that it takes a signal, for example, in this case, an audio signal, and decomposes it into the series of sinusoids that make it up. Now, the result of this function is the signal on the frequency domain instead of a time domain. Now, what this means is that you'll produce a graph. On the x-axis has a series of frequencies which correspond to different sinusoids, and on the y-axis you'll have the magnitude of said of frequencies, which should tell you which sinusoids are the loudest, or comprise of or have the highest magnitude within the function. So let's say, for example, I listen and play a 250 Hz tone very loudly. And wait for it to finish processing. And here is our result. You can see that on the y-axis, we have the magnitude of each sinusoid. On the x-axis, we have the frequencies of each sinusoid. And you can see the highest one, as indicated here, is 244 Hz, which isn't exactly 250 Hz, but it's fairly close given that we have a lot of ambient noise in our environment. We have, me talking. We have, we have the air ducts running. So this isn't precise, but from what I've measured, it shouldn't be more than a 5% margin of error. Likewise, if we play, say, a 300 Hz frequency, and run this, and again, give it a second process. And here we go. You can see the highest frequency is at x equals 294, which is, again, within that 5% margin of error. Now, graphs like these are a really good way to visualize any input sine wave and really show what the Fourier does and what its Fourier transform does and what its purpose is. But the problem is that this is just a plain graph. It's not very engaging. So what I'm going to try to do instead is have a drone fly along this locus of points and show, say, to an audience or to a larger group of people just what the Fourier transform does using a more visually engaging method. Here's the Fourier transform graph from that 300 Hz tone that we just recorded. Now, it's important to note that this is normalized the values are normalized between 0 and 80 because, the drone's going to be flying this path, and, I don't have infinite space in this basement. So now what you're going to do is send these as a series of coordinates to the drone in order to have the drone fly these out and show to just a general audience what the composition of the signal looks like. Right, so uncomment this. This is what actually sends the set points to the drone. And I'm going to take off in 3, 2, and 1. Right, now we're going to send some set points. Again, moving along with each point on that Fourier graph. So once it hits 80, then it's going to go back to the origin and then land. Or I'm going to land it. See, it's hit 80. Now it's slowly going back. Just to, avoid it starting quickly when I land it. What's also important to note is that since we have the magnitude, the frequency, and the phase angle, which was calculated separately as the arctan of sine over cos or imaginary over real, we actually have all the elements necessary to generate the sine wave ourselves. So if, say, a user someone wants to see the full sinusoid, that being at 300 Hz where magnitude is greatest, we can actually fly that out for them too using the drone. So here I've substituted the normalized x and y for the x and y of the generated sine wave, which we now send to the drone as a set of set points for it to fly along. So again, once we get it started, and then send it some set points. You can see it flying the sine wave, moving periodically. Should note also the frequency is normalized between 0 and 100, so it isn't exactly 300 Hz because that would just kind of look like an incoherent mess. And reaching 80. You can see it traveling back. And we're just going to land a bit early.